Okay, welcome back. So in last class we observed that how to write the VHDL program for different logic gates in different architecture models. For example, the slide showing the VHDL representation for the NAND gate, right? In the NAND gate, that in which model? Data flow model. Okay, so here in the data flow model, the statement is signal assignment statement. So z less than equal x NAND y. And also we observed that how to show the behavioral representation for the XOR gate. Okay, so in XOR gate case, for the behavioral architectural representation, truth table information we need, right? So this is the entity declaration for the given XOR gate. Okay, so entity XOR2 is port of two inputs XY in standard logic, Z is out standard logic, and XOR2. Like that we have written entity declaration. And coming to architecture representation in the behavioral model. Okay, so this is the truth table for the XOR gate. So by observing this truth table information, the output of XOR gate is 0 when both the inputs are equal. When both the inputs are equal, the output is 0, otherwise it is 1. Okay. So therefore, the programming part, coming to programming part in the behavioral model, the architectural statement is process. Okay. In the behavioral model, compulsory, the statement type is process. So process of x comma y as per syntax, then process begin, then the sequential statement which I have selected here is if statement. Okay, if else and if statement I have chosen for representing the behavior of the XOR gate. Okay, so how I have written it is if x equal to y. So if both the inputs are equal, then the expected output is 0, right? Otherwise the output is 1. Okay, so through if statement I mentioned the operation of the XOR gate, then end process and architecture name, that is behavior. So up to this actually we have seen in last class. So once again I discussed here, and now coming to the next part is, that is combinational circuit analysis. Combinational circuit analysis. So with reference to this, I have given already what is combinational circuit. In combinational circuit means the outputs always the function of the inputs only, current inputs. Output is always the function of the current inputs. That is called the combinational circuit. Now we are going to analyze this circuit. So in the analysis, first of all, we need to derive the equation by linking outputs with the inputs. Okay, that is we are framing the logic function between outputs and the inputs. Okay, so here one circuit is available. With reference to this logical circuit, how can you relate your outputs with the inputs? That we have to see first of all. In that case, in that relation development, the first step is you need to show the Boolean equation at the output of each and every gate of that digital circuit. Okay. So here how many gates we have? 6 gates we have. Okay. So first of all prepare the 6 gate output Boolean equations. After that the final equation in terms of primary inputs. Okay. So in that way, what is Z1? What is Z1? First of all, Z1 is shows the AND operation on inputs x and y. Okay, it gives AND operation on inputs x and y. Therefore, the Boolean equation is Z1 equal to xy. Okay, Z1 is xy. Similarly, coming to Z2 shows the OR operation on inputs x and y. Therefore, the Boolean equation is x plus y. Then coming to Z3 gives the NAND operation on inputs x and y. NAND operation. Hence, the Boolean equation is x dot y whole bar. x dot y whole bar. Similarly, Z4 is the complement of y input, the complement of y input, therefore Z4 is y bar. And coming to Z5, it gives the XOR operation on inputs Z1 and Z2. XOR operation on inputs Z1 and Z2. Therefore, Boolean equation is Z1 XOR Z2. And finally, the Z is the NOR operation, on inputs Z3, Z4 and Z5. Okay. Then the Boolean equation is Z5 plus Z3 plus Z4 whole bar. Okay. Now we are going to show the output Z in terms of X and Y, in terms of primary inputs X and Y. That is, what is Z5? Z5 is Z1 XOR Z2, but in terms of XYs, where Z1 is XY and Z2 is X plus Y. Okay, so therefore instead of Z5, we can write it as XY XOR X plus Y. Okay, it is XOR operation. It is a XOR operation. Okay, XY XOR X plus Y plus Z3 is the NAND operation on XY. So XY whole bar plus Z4 is complement of Y. So Y bar. So whole bar. As per the Z, whole bar it is. So like that, the equation is, the logic function can be derived for the given logic circuit. Okay. Then after that, is it clear all of you? Okay, how this equation was derived? Okay, I think you already did the such type of derivations in the DLD subject, that is digital electronics and logic design case. The same thing we have seen once again, that's all. Then coming to Boolean identities or Boolean algebra, so which is helpful for the minimization of the Boolean equations, so that minimization of logic circuit. Okay, so always you need to design the logic circuit with minimum number of gates, so that the complexity will be reduced, the cost will be reduced, the power consumption will be reduced. Okay, those are the advantages. That's why always you need to design with minimum number of gates. Okay, so for minimizing the Boolean equations or logic circuits, there are different techniques. One of the technique is using Boolean algebra. Okay, Boolean algebra. So first of all, coming to Boolean algebraic identities, Boolean algebraic identities. Okay, so those are with reference to OR gate and AND gate. The identities are represented like this. So adding 0 with x gives x, adding 1 with x gives 1, adding the x variable with x gives x, adding the complement of x with x gives 1. Similarly, multiplying the x variable with 0 gives 0, multiplying x variable with 1 gives x, like that x into x is x, x into x bar is 0. So these are the these are treated as the identities of Boolean algebra. Identities of the Boolean algebra. Okay, so with reference to OR gate and with reference to AND gate, the identities are listed in this table. Okay, that is with the OR operation, with the AND operation, what is the expected result on the given variable, like that the identities can represent. Okay, now showing these identities as a VHDL program. Okay, already you know, before going to write the entity declaration and architecture body, first of all you need to open the desired library, that is IEEE. So the first statement is library IEEE. After that, from the library you have to choose one package, standard logic 1164, and from that package all the declarations whatever available, those are should be in effective in the following program. So that's why it is written as use IEEE.standardlogic1164.all. Then coming to entity declaration, So entity declaration, syntax already starts with the word entity. Entity syntax starts with word entity followed by the name of the entity, that is Boolean identity. Boolean identity is. Then declaration of inputs and output ports. Here only one input, that is X. So port of X colon in standard logic. But two different outputs with reference to R identities and AND identities. So Y R identities, Y AND identities are the outputs. In each output case, in each output I declared a vector or array declaration I have given for each output case with size 3 down to 0, then end Boolean entity, that is ending the entity declaration. Okay, next is architecture. We have to write. So architecture start with architecture name, the word architecture, then architecture name, data flow of Boolean identity. Boolean identity is the entity name is. Then in the architecture case, here some declarations are there, two declarations. One is constant, name is 1, data type is standard logic, and initial value is 1. There is another declaration, name as 0, that is constant 0, with the data type is standard logic, and value also 0. Value is 0, initial value. Then begin. Okay. So begin, now I am going to show each and every identity operation whatever we observed in the truth table. Okay. So y r of 0, okay, that is what it consists. Y r of 0 location, since y r is declared as an array, it has 4 locations. Y r of 3, 2, 1, 0. In 0, what is the expected output? That is XR0, that is x plus 0. From the truth table, it is equal to x plus 0. Okay, x plus 0 result will be saved in y r of 0 location. Okay. Next, y r of 1 equal to in which result will be stored in this location means XR1. Okay, so XR1 means x plus 1. Then XR of 2 in this location, what is the result will be loaded means with XR X. Like that. Similarly, YR of 3, XR not of X. That is x plus x bar. Result will be loaded in the third location. Okay, so like that the output YR gives as per the truth table the different operations result. Similarly for AND gate. Okay, so all the 4 operations we represented, and finally end architecture name. End architecture name is DF. Okay, so in AND operation also we have 4 expected outputs, that is ANDing logic 0 with the input variable x, ANDing logic 1 with the input variable x, and ANDing the variable itself and complement of variable with its virtual value. Those are loaded respectively y and of 0, y and of 1, y and of 2, y and of 3, like that. Okay, so like that the entities Boolean entities with reference to OR gate and AND gate we can list out in the truth table, and we can develop the VHDL program for it. Okay. Thank you. Now I am going to stop this session. In the next class we will see the another topic. Okay, thank you.